Hello guys, welcome to the video. So in this video I will talk about I get some emails and stuff, LinkedIn DMs or something from some of you guys. I mean, I don't know if all of those guys watch my YouTube, but still I think it's a very important question to discuss in general, and that's why I'm making this video. And As you can see, I don't know, I'm recording full screen because I want to show you some other stuff as well in this video. I mean, relevant stuff, but some, uh, I don't want to screen share on my Google Meet because I'm anyway screen recording. So I just I'm recording the full screen. And if you can see in the bottom right corner of the screen, it's 3:13 in the night, the time right now. Okay, the time of recording the video, and today is 20th July, so I don't know when I will be able to upload the video to YouTube because there's a queue. Some videos are, I upload my videos in order, so one or two videos I think should be will be uploaded before this video. So by the time this video will be posted on my YouTube channel, maybe it would be 27th July or I don't know, 25th or 27th July, whatever, maybe before. But in this video, I want to discuss basically. So if you want, yes, let's say you want to be a physicist. That's the question people ask me that, Arpan, do you have any advice or any suggestions? Because maybe I am a high school student, I'm a grade 8 student or standard 8, standard 9 student, or I'm currently a standard 10 student or 11, 12 student and I wanted to become a physicist. Any advice? First of all, I am not a physicist myself. I don't yet have a PhD. I will be just be starting my masters in a few days time. So I myself I just am a BSc physics graduate. So I'm not an expert by the standards of by the conventional standards, by the standards set by the system. I am not a physicist. And do I consider myself a physicist personally? The answer is no. Do I consider myself a true physics lover and and an explorer of physics? The answer is yes. I mean, that's what I consider myself. But of course, one cannot judge oneself. But I personally think I am a true physics lover and at least an explorer of physics. Whether I'm a physicist, well, I don't think there can be any definition of physicist, and I think the question is somewhat meaningless because, yeah, once I will have a PhD and maybe some research positions and all, then of course officially I can claim that I'm a physicist one day in the future, hopefully. But that doesn't make any difference to, because in my experience at least, your university degree, the university we're going to, and all of this stuff, don't really really matter. It doesn't really define your motivation for the subject as well as your understanding of the subject. Those are important because without those stamps on your CV, on your profile, nobody will care about you, and you will not get a job. You will not, and also not the job part, the financial part. The job part is the most important part, but even apart from that, you need some institutional recognition and some institutional affiliation, because without an institutional affiliation, even if you do some real original work, some respectable work, nobody's gonna take you seriously, and that will act like a negative feedback, feedback loop, and you will slowly lose your motivation for the subject. So that is also important because there are a lot of things in the system which are not right, which needs to be changed, but it is still the system that can validate your work. You cannot yourself validate your own research, not to the full extent, at least. I think you will agree, and that is true, no point denying that. So my point is, since I am not a physicist by the official, by the usual, by the conventional standards, I am not really aware about the exact path. I mean, of course, I'm aware about the path, but I have not gone through the PhD postdoc journey myself yet. So once I do all those stuff, maybe I will be in a better position to give you advice. Of course, you should not wait, because there are a lot of other people out there, physicists, physics professors, or even some other people who are much more qualified than I am, who can give you actually more practical advice. I will give you some advice in this video. That's what I'm making the video for. But those are just my personal suggestions and my personal story, and I have had reasons to believe that the way I have developed myself, my thinking, my understanding of physics is might not work in general, because it has its pros and cons. So I don't want to put this forward as general advice for anyone who wants to be a physicist. But first of all, I don't know you personally. So when you say I want to be a physicist, what is it that you actually want? Is it you want a good job in a good university and you want to become a physics professor, or you want to have thousands of publications, or you want to do some groundbreaking work and get a lot of fame and recognition, or you want to work on the foundational aspects of physics or on applied physics? And what is your background? What are you like as a, what is your personality? If I don't know all of that, I cannot give you personalized advice. Advice cannot be the same for everyone. But I could share some general points definitely, and that is what I plan to do in this video. Okay, so please excuse this because I'm feeling sleepy. Plus, I have developed a slight cold kind of thing, so I don't feel like talking a lot. But I have to talk a lot for making this video, and that's why I just have a hot cup of coffee with me. And now is the best time because in the morning with all the chaos and noise everywhere, it's not a time for recording these kind of videos. Plus, now I'm just myself in my room, just with my two of my laptops and just my stuff, and it is nobody's here to disturb me, except this occasional this urge to go to bed and just switch off the laptop, turn off the light, and go to sleep. Other than that, there is no disturbance in the night. That's why I like working in the night. Anyway, so if you want to be a physicist, first of all, I'll tell you the bad. I will tell you the downsides. I will tell you the potential problems that might arise, and then after you listen to this part of the video, if you still think you want to be a physicist, listen to the rest of the video. And after listening to this part, if you think no, maybe I don't want to be a physicist anymore, you can like not watch the rest. Okay. First of all, becoming a physicist is, in my experience at least, this passion for a subject, especially for a subject like physics, especially research and this kind of thing, it's very, in most cases at least, it's very short lived. Let me tell you what I mean by that is that in my case, I still love physics as much, if not more, as I used to do 6 years back when I first decided to explore physics. But my view of physics and my view of a life in physics, a career in physics, or the kind of problems I plan to work on, or the kind of problems I thought I would explore 6 years back, and the kind of problems I am exploring or I plan to explore in the future now, that has changed drastically. So initially, my interest in physics stemmed from reading popular science books and this quantum mechanics stuff, which is kind of obvious, not very obvious because most people usually get interested in astrophysics and cosmology. A young guy, that is the first thing he or she, that's the first thing they wonder about in most cases. They look up at the night sky and what is that? What are those stars? Twinkle, twinkle, little stars. How I wonder what you are, and what are those? We are just in space and all this. These tales. These facts which we usually feed to the minds of the like the maybe the 5-year-old or 6-year-old. Like, do you know that the Earth is spinning around in space, the sun and all the Earth is revolving the sun, and there are the stars and all this. The universe, it came from the Big Bang. There's a theory called the Big Bang. This catch their imagination because they are at the same time very interesting and somewhat digestible in the way because you can see the stars and you can want to see the vastness of the night sky with your eyes. You don't need to solve equations for that. Just to appreciate the fact, you don't need to solve equations. Now, quantum mechanics on the other hand, if I try to explain quantum mechanics to a 5-year-old kid, do you know that when you look at atoms, excuse me, what are atoms? No, if you go keep on breaking stuff, you will reach a very small, indivisible, not really indivisible, but something very small units of which everything is made of. So those are called atoms. Oh, okay. So are there something like Lego blocks? Maybe Lego blocks, yeah. But what I'm saying is that did you know that these atoms or even these atoms are made up of even smaller particles called electrons and subatomic particles. So do you know that you cannot know the position and momentum of an electron simultaneously? Wait. What is position? What is momentum? Okay, so suppose you are an electron. This is your position. That means you are right now in this room. You are not in the next room. That is, I am sure about that. That is your position. Now, if you start running, you will have some momentum. If I start running, I will have some momentum. But what is momentum? Well, it's something you have when you move, when you have a velocity. Wait, what is velocity? Uh, I think you understand the difficulty of explaining quantum mechanics to a 5-year-old kid. These are not intuitive concepts. They cannot feel it. A particle and a wave at the same time. First of all, wave particle duality is not the right picture to introduce quantum mechanics, I personally think, because superposition principle is the best, most fundamental, and most logical feature of quantum mechanics. The wave particle duality, these are all just a way of speaking. But anyway, even wave particle duality, a 5-year-old kid cannot grasp, leave alone superposition principle and everything. On the other hand, if you tell a 5-year-old kid, look up at the night sky, those are the beautiful stars, you know that those are actually very far away from us. That's why they appear so small, tiny dots, but they are huge balls of, like burning gases, and they're giving off light and heat. This is such a beautiful. I think it's much more, at least as compared to quantum physics, it's much more relatable, even to a young student, 5-year-old kid or something. So that's why people are usually gravity. You can see you drop an apple, it falls down. You can make this explain. But electromagnetic radiation also, you cannot really give the feel of electromagnetic radiation to a 5-year-old kid. What you can do is, okay, you just rub a comb on your hair and then you just show this that all those kind of basic experiments, those pieces of papers they stick up, and that's because of electricity. You can show them, and maybe they will they will get to see interesting stuff, but they cannot really appreciate what electromagnetism really is at 5 years old. Even on 5 years old, true electromagnetic theory is actually very complicated. If you go to the Maxwell stress energy tensor potential formulation, actually the way it was mathematically formulated, the beautiful way Maxwell did it, that's even you will not be able to appreciate the true beauty before. I mean, you will be able to do it only when you're an undergraduate student in physics. But not everyone decides to study physics undergraduate, of course, and that's okay. I mean, that's not, physics is not for everyone, because if everyone starts doing physics, then who will do the other things? I mean, physics is not the only thing that we need. We need everything. So I mean, you get my point. First of all, you ask yourself. See, those of you who are asking, who that I want to be a physicist. I'm currently a high school student. I'm currently this, that. What should I do? First of all, ask yourself, why do you want to be a physicist? This is very important advice. I'm not trying to discourage you. I'm trying to give you a reality check. If you can pass this check, it's, see, you don't have to comment on this video, or you don't have to tell me that, okay, Arpan, I passed this check. I am not your judge. I am not your validator or anything. I'm nobody. You don't have to inform me, or anyone for that matter. It's your own decision. It's your personal decision whether you want to do physics or something else in your life, because it's your life. You just ask yourself that, okay, so Arpan asked me to think about it deeply. Let me think about this deeply. Why do I want to become a physicist? And after thinking, if you think that this is a valid, I mean, if you still pass the reality check, you go ahead with physics. If not, you don't have to inform anybody, but you can think of something else. The point is, you ask yourselves, why did you choose physics? I mean, all of a sudden, why do you want to become a physicist? And again, I'm not saying this to discourage you, because physics is a very interesting subject, and as compared to the many other career paths, physics also has a lot of scope. Even considering today's current scenario, that there is a lot of competition in academia, it's very difficult to secure funding. All of those are very valid concerns today. I mean, not just in India, all around the world. But even considering all of this, I think physics is a much more safe option. I mean, it's a better choice than many other career paths. That is also true. Again, of course, it's much more difficult also as compared to some other career paths. So physics doesn't come for free. So my point is, if the answer to your question is, okay, why do you want to become a physicist? Suppose you ask yourself and you answer yourself. This is just you're talking with yourself. You don't need to inform this to anybody. There is no question of, like, validation or anything. Just talk with yourself. You can be totally honest, because you're talking with yourself. You don't need to tell anybody about this. So if the answer to this question is, oh, I suddenly I watched a movie, and maybe I watched Avengers Endgame, and I was like, oh my god, quantum mechanics, time tunnel, time travel, and I was, oh, I wanted to become a quantum physicist. Or I read a popular science book, I read a documentary. If that is your answer, then I'm not saying you should stop thinking about becoming a physicist, but you should explore physics much, much more deeply before forming a conclusion that, no, I really want to be a physicist and not something else. Now, by that, I don't mean you should start reading undergraduate textbooks in physics when you were a high school student. Even I did not do that. I read much advanced stuff compared to my age. When I was in the last 4 years of my high school, like I actually read Schrodinger's equation, and I started reading basic perturbation theory when I was in class 10, which is advanced topic. But I didn't follow any rigorous undergraduate textbook, or I didn't, follow any very much technical. I didn't take pressure. I was just exploring the stuff. I loved it. I was exploring. That's what I'm saying. You explore physics at your leisure. If you're a high school student, if you're an physics undergraduate, I don't think there is a question. They definitely want to be physics. Not really. After a physics undergraduate degree, you can do a lot of stuff. It's not that if you have a physics undergraduate degree, then you have to be a physicist. You can do a lot of stuff. But anyway, so if you're a high school student and you're considering a physicist as a career path, then you explore, you read some popular science book. Reading is fine, and also important at your stage, because at your stage you cannot and should not read textbooks, because you have a lot of other I mean, exams to give. I mean, I know those exams are not really important, but still, if you cannot pass school, you will not get into undergraduate program. So like it or not, that is the system. So I think you can explore, you can read popular science books, and more importantly, you can, because especially today this is much more relevant, you can go to YouTube and watch some physics videos, because popular science books, I'm telling you the reason. Popular science books, or any book for that matter, is a long, I mean, you need to invest a lot of time to, if you decide I will read a book. A book is usually like, I don't know, even popular science books are 300, 400 pages, the good ones, even more. So along with your school studies, along with other, if you decide to invest so much time into reading a particular popular science books, the problem with that is, one popular science book is being written by one single author, and that book will definitely contain only the views of that author. So you are being exposed to one particular viewpoint, and you're spending so much time on that, so you might get biased, and you are reducing, you're cutting on the time you have to explore other viewpoints. The good thing about YouTube, if you can avoid the distractions and if you can find the right channels, because there are a lot of rubbish stuff on YouTube as well, like rubbish or pseudoscientific stuff, which are presented as authentic science. So you should be careful about those. Books. The good thing about popular science books, especially the famous written by famous authors, published by respectable publishers like Penguin, Random House, and all. The good thing is that you can at least trust whatever is written in the book. It's written by a respectable author. YouTube, well, anybody can upload anything. You have to filter the what is authentic and what is not for yourself. That's good in one way. You are gaining experience in filtering information, because the world today is filled with misinformation and disinformation. But yeah, you have to be careful. But the good thing with YouTube is that you don't have to invest a lot of time, and you can simultaneously explore different viewpoints. Suppose you want to understand what is quantum superposition, and there are a lot of YouTube videos. You just search quantum superposition, press enter, and then you get a lot of videos. And these videos, you don't need to invest as much time as reading an entire popular science book. So you watch all of these videos. I mean, you shortlist the 5 or 6 best videos on the topic, look at the views, the channels, and all, and you watch 5 or 6 of them. So you get exposed to 5 or 6 different views, and you form your strong concept in quantum superposition, or whatever you were looking in YouTube. That's a good thing, right? You can also look at real-time comments and all. Most comments are usually not nonsense, but some comments are, from like might are interesting, and also it's a much more, and also YouTube is a much more, like popular science books published maybe 15 years back, or most likely they're outdated now. YouTube, if you regularly follow some really good, there are some really good channels in YouTube. Very few, but yeah, if you follow these channels, you can actually get you get stay updated with a lot of research. And most of these channels on YouTube, they present stuff in a for the general audience. So even a high school student can follow and develop their interest. If you're already a researcher, you don't need to watch YouTube videos, this kind of videos. That is one thing you can do. And after doing all of this, my only my I will be sharing 2 or 3 suggestions with you. I won't say advice or thing, but you could take this as personal suggestions. The most important of which is, don't get, it's very difficult to avoid. This trap is very difficult to avoid, but still I'm telling you, don't get stuck in one particular direction, or if I put it, one particular branch of physics. Let's say you want to be a physicist. You start exploring some topics, and suppose your interest is caught by astrophysics. Suppose, it could happen. It could be astrophysics, quantum physics, whatever. But now, so at this point of time, maybe astrophysics is the most interesting to me. I also a little bit explored quantum and all that, not really my thing. So let me just choose astrophysics and explore it much more deeply. Do that, no problem. But high school, or leave alone high school, even undergraduate is not the time to choose your specialization, in my opinion, because you're not really at a position to make an unbiased decision at this stage. So you like astrophysics right now, just giving an example, maybe because you your mindset is more towards that, and you have been exposed to that in a more beautiful way, or you have formed some misconceptions about the other branches of physics. But the problem, if you just follow astrophysics, go deep into it, and totally ignore the other branches, the problem might be that in the future you will have no other plan B. If you suppose sometime in the future you no longer like astrophysics, and you want to change to some different area in physics, you will not have that knowledge. You can develop it, of course, but it will be difficult to do it then. So it's always a good idea to, number one. Number two is that, it's very very subtle comment. I mean, this is a very some people might think this is not a very good suggestion, but the reason I believe in this is, I'll tell you the reason. Now, whether you follow it or not is up to you, because again, I'm not sure whether this will work for you, because I mean, at some point, deciding your path is also important. Otherwise, you'll be confused. Oh my god, I like astro, I like quantum, so what will I do in life? That's not the thing. But personally, I think it's also very important for a physicist or a physics student to try to connect the different branches of physics, because at the end of the day, what we are trying to do with physics is describe the universe around us. Maybe somebody is looking at the universe at the astronomical scales of galaxies, planets. So in those length scales, gravity is the most dominating force, and they're looking at gravity, gravitational waves, and all this stuff they're studying. Those are the really the interesting areas in astrophysics, gravitational waves and all. Otherwise, the people who are doing the stuff like experimental astrophysics is something I have never liked, but I won't say they are not important, because I cannot say that. Because if somebody says quantum mechanics, quantum foundations, quantum measurement problem is not important, statistical physics is not important, nonlinear dynamics is not important, dynamical systems theory is not important, then I will feel very bad about it because those are the areas I work in and I like. So I should not and I will not make any claims. But personally, I don't find that interesting, and I think the real work in astrophysics is in gravitational waves and astroparticle physics, because there are some areas in astrophysics like working on extensions of the standard model of particle physics, which is actually a particle physics theory, the standard model and quantum field theory actually. But you need some astrophysics and stuff, cosmology actually, not astrophysics, cosmology, to study dark matter models and all. So those are the how did the symmetry breaking happen in the early universe, studying the early universe basically. Then isotropy of the early universe, not, I mean, isotropy means isotropy and homogeneity. So if you think about it, it's the why the early universe was so smooth. It's not actually isotropy homogeneity. Isotropy homogeneity are just some assumptions in cosmology, Newtonian cosmology especially. But I'm saying why the early universe was so very smooth. Well, there's a lot of theories, inflation theory and stuff, but these are the real questions you need to study. And this is more, I think this is more cosmology than astrophysics. Astrophysics is more like computation and data. I don't find those. You're not really adding to knowledge. You are just finding it. You're just working with some data, fitting it, and maybe you appear to be a very good, doing some very good technical work. Not really doing something. That's the my personal view anyway. But if you find that interesting, of course you can go forward with it. It's your decision. The point is, it's always important to connect the different branches of physics. Now, some people will say that no, you have to decide one. You cannot be good at a lot of things. That's the advice I get all the time. Arpan, you have been doing quantum mechanics for the last few years. Suddenly, you shifted to statistical mechanics and nonlinear dynamics and biophysics, active matter physics, study of biological systems using physics. In the last 1 year, suddenly this abrupt change. Why? Because you have done so much stuff in quantum mechanics, publications, projects exploring quantum mechanics, written a book on quantum mechanics in such a young age. You should pursue quantum mechanics. I mean, when I was doing all those exploration in quantum mechanics, did I sign any agreement that no, I will be exploring quantum mechanics in my master's and PhD? Am I under any obligation? And who said that somebody cannot explore quantum mechanics and statistical mechanics, or quantum mechanics and the physics of complex systems? Who said that somebody cannot explore these two simultaneously? Because at the end of the day, physics is about the universe. First of all, you have to understand what is the nature of physical law. Statistical mechanics, not statistical mechanics, is my personal philosophy actually. I believe the universe does not follow the laws of physics. Like the apple does not fall because of Newton's law. Then why does the apple fall and not rise up? See, I have a habit of explaining everything in terms of entropy, but even entropy is a statistical law. The second law of thermodynamics is a statistical law. If you go deep into it, you will see there are a lot of loopholes. Like Boltzmann brain hypothesis, if you read it, the Boltzmann brain hypothesis is itself an incorrect hypothesis. It seems incorrect as of now. But still, it will give you a very good idea if you follow Boltzmann's argument, the thought experiment. It will give you a very good idea about why even this is a very deep question, the early universe cosmology, why the universe was so smooth, the early universe was so smooth and all. And like maybe our universe is a low entropy fluctuation from a much this kind of strange hypothesis, Boltzmann brain and everything statistical, that will actually show you my advice would be to you would be this: if you want to become a physicist, start with any one question. Maybe first of all, if you don't have any preference at the on day one, you start with any random question, physics question. I mean, not the textbook question. It could be any question. No question is stupid. See, no question is stupid. If you ask why the cup, suppose if I throw the cup and it breaks, now why doesn't the broken cup repair itself? If you ask this question, apparently it sounds like a very stupid question. You are a student, you are a high school student. Is this magic? I mean, why are you asking questions like why doesn't a broken cup repair itself? Of course, a cup is broken. How will it repair itself? How will it just repair by itself? Question sounds very stupid. But this question actually hides a very important question which is still unsolved in physics. That is the question of arrow of time. Because in quantum mechanics, the equations of quantum mechanics are time symmetric. So you expect that if an event happens A to B, then the probability of the reverse event is also equally likely in quantum mechanics, at the level of atoms and all. But for cups, like for this cup or for microscopic objects, that's no longer true. So let's say I have a paper here. So say this is my state A. The paper is intact. Now I teared the paper and this is my state B. It's in two pieces. So the probability from A to B, I mean, you at least forget probability. You saw with your own eyes that I can go from state A to state B. Now, if I say that I want to go from state B to state A, I want to join this paper together. Can I do that? I mean, of course, I can maybe put a sellotape or just stick it together by some glue or something. But can I exactly get back this intact state A? Anyhow, I cannot, right? So all this is related to statistical mechanics, entropy, area of time. I will not go into those technicalities in this video. That's not the point of this video. And I discussed this stuff in one or two of my previous videos as well. If you're interested, you can take a look at my channel. Point is, this is a question. If you explore this deep enough, you will be led. I think you will be led to an area which lies in the intersection of statistical mechanics and quantum mechanics. Now, within statistical mechanics, there are some sub branches where you don't need to use or know the foundations of quantum mechanics. But if somebody says that no, you cannot do stat mech and quantum mechanics simultaneously, why not? I mean, why not? At the end of the day, everything is connected, and physicists expect that everything should be explained by the same approach. Now, some physicists say that there is a theory of everything, unified picture, the universe is completely deterministic and follows the laws of physics. I don't completely agree. Actually, we are not in the position to make any comment on this because we know very little. Could be deterministic or could be what I think, but we don't know enough to make any claim at this point. So I'm not making claim. But personally, I think, like I was saying, the universe doesn't follow any law of physics. You understand my point? Uh, the apple falls down because this behavior is in sync with the evolution of the universe. Because when the universe is evolving the way it is doing, it's expanding, so the entropy is increasing, then the structure formation. So this is happening now. My understanding, I mean my belief, rather not understanding, my view is that we cannot exactly answer why the universe is evolving the way it is. So it's kind of, I won't say it's beyond science, but I think within science it falls to those questions which are unknowables, kind of. I mean, whether it's science or not science is an open question, but I think we cannot answer the questions because it's impossible for us to know the initial conditions of the universe. Because how will you know it? You cannot do an experiment that will give you the exact initial conditions of the universe. We don't even know whether the Big Bang theory is true or not. That's the most likely theory which has been validated experimentally. But even it's not like not a fundamental. Nothing in science is permanent or absolute. So if we cannot really know the initial conditions of the universe, then how can we ever, we can build theories, we can build models, and some aspects of those theories maybe we can even get experimental validation, but we cannot be sure that this is the right. We cannot ever be sure that this is the right. And without experimental validation, without complete experimental validation, and without complete reproducibility, and all these basic falsifiability and basic tenets of scientific for an hypothesis to be a scientific hypothesis, how can you be sure that this is actually you're doing science and not philosophy? Then if you cannot answer, then accept that it's a brute fact. The universe evolves in this way because the universe behaves like this because that is the way it is. Simple. It is what it is. Stop there. If you want to go ahead, you can do that, but then you will be philosophizing and you will not be doing science. Now, my point is, I'm not saying we should stop trying. A lot of problems that needs to be solved, and some of those problems are much more closer to us, like biological physics. How does the cell work? Self-organization, assembly, and these are all kind of, you need statistical mechanics, you need entropy. You need a lot of these concepts, and if you, maybe somebody also need quantum mechanics. Photosynthesis in trees use quantum mechanics, and everything. You need everything actually. If you want to know it deep enough, it's not like you don't need. Okay, I'm doing biophysics. Why should I learn quantum mechanics? It's not like that. Cosmology. I am a cosmologist. Why should I learn stat mech or thermodynamics? Stat mech and thermodynamics is extensively used in cosmology. Black hole information paradox. Black holes, where the understanding of black holes was drastically changed once it was hypothesized that black holes have an entropy. This is not exactly the same entropy we usually think when we talk about entropy. But this idea came from the entropy in stat mech, right? Thermodynamics and all. Even the universe is treated as a closed system. Universe as a box of gas. So you're using thermodynamic principles there. When you say the entropy of the universe is increasing, it will be the maximum when the universe is in the heat death of the universe and all thermodynamic kind of time. So it's all related. There is I think you will not be able to find a single branch of physics or a single, not even branch, a single, even a narrow single area of research or a single question of physics that is entirely and totally isolated from the other branches of physics. Somehow or the other they're linked. Maybe we have not even connected all the dots, we have not discovered all the links, but even today we know enough to see that everything is linked to everything else. And on the contrary, since most people follow the tradition, like, I want to do this, so I will just specialize in this and totally ignore the other branches. If you but of course you have to specialize in only one branch, but if you Instead of ignoring, if you just try to connect whatever you know in your area of expertise with at least with the basic structure of some other theories in physics. I mean, as a physicist, you should at least have basic idea of everything, not just even if you are doing stat mech, you should have some basic idea of quantum mechanics, right? So if you try to relate thing, then I think you will be at an even more better position to make some unique connections and do some real unique significant work, not just some data analysis or some computational work, some real work. So I think that's a very important advice. So start connecting the dots. Now I'll give you some examples. I've been saying this, connect different branches of physics. But what we actually mean by that, I'll give you some examples. That's why I'll show you some thing also. I have these tabs open as well in this video so that you can appreciate what I mean by this. Before that, see, in my case, my if you consider my story, I was initially into consciousness. If I go to if I go to my initial days, like 6 years or 7 years back in my high school days, I was like so much bewildered by what is consciousness? Why am I conscious? Who am I? What are my feelings? I couldn't make a sense of it, and it was not just curiosity. A lot of people think that I came to, like, scientists study science because they're curious about the universe. Maybe that could be true for a few scientists, but I think at least for people like me, I think that's not the case, that I am curious, that's why I'm doing physics. For me, it is like an absolute necessity to answer these questions. I know I will not be able to answer what is consciousness in my lifetime. Maybe nobody will be able to answer that. There are some fundamental limitations. But at least I can say that I tried answering the question, I tried exploring this question instead of doing a conventional job and living a normal, ordinary life that all the other humans are doing. So without this, my life would be meaningless to me. I would not have enough motivation to live, no matter whether I did a $1 million job. So that is the reason I came to physics, not because I was simply curious about the universe, but because these questions kind of haunt me, bewilder me. Like, oh my God, how is this possible? At least I should try to find out the answer. Even if I, even deep inside, I know that these answers are not like I will be able to find out after 2 years of research or something. But that is it's not just curiosity. I think it's more compulsion than curiosity. Otherwise, these questions will always haunt you. At least in my case, I cannot tell about you guys, about the others, but in my case, that's the thing. So it started with consciousness, and then I suddenly stumbled upon physics, and then I developed this interest in quantum mechanics. I think that is the reason. Because if my interest in physics started when I was very young, like maybe 5-year-old kid, then of course, in all likelihood, I would be exploring astrophysics instead of quantum mechanics. Since I came to physics in a much like when I was in class 9, I started exploring, and then of course I was not an expert then, but at least I could make better sense of quantum mechanics than a 5-year-old kid, and that's why I that interest caught on. And for some reason, I never found astrophysics interesting. I am really mesmerized by space and all this stuff, but I don't think that is much more interesting than this brain. What is sitting in brain, or this complex human body, the way these interactions are happening, and the way I'm alive and able to live a life of 70 years, 80 years, humans are able to live. And I think this is a much more bigger mystery to me than, oh, there is space, or there are stars, there is space. Okay, so it's very strange, very mysterious, but I think I am just my person. I am much more interested in this. And then quantum mechanics. Quantum mechanics, I think, is the branch of physics that comes closest to philosophy, because quantum physicists have explored these questions of deep questions, like existential questions, because you are going deeper. Even cosmology has birthed a lot of philosophical ideas. When you think of the universe, that's also philosophical in a way. That this it allows you to explore, think about the insignificance, that you're just an atom within the universe. If you think, and in that, if you blow an atom up to your size, then the universe would be you know what I'm saying. But at your level, you yourself are a universe of atoms. You're made up of billions of atoms. So that's the beauty. That's the different scales, different length scales. That's the thing. And, yeah. So my advice to you would be, think. You start with any random question, go deep into it, as deep as you can. Suppose you start with a question. Let's say, suppose you're reading electrostatics in your high school or something, and your first question is, what is charge? Okay, most people are okay. In the book is written, charge is some inherent property of a particle. It can either be positive or negative. So this is charge is this positive or negative, and this is that's charge. I'm satisfied. Let's move on. Next is, what is electric field? What is potential? No, don't do that. If you want to become a physicist, a true physicist, don't do that. Stop and ask. Charge is an inherent property. Okay, but what is an inherent property? What is charge? I understand it's plus q is a positive charge, minus q is a negative charge. But why are there only two types of charges and not three types of charges? Why, I mean, how can we differentiate between two types of charges? Of course, people have seen that some particles behave in a way which is opposite to some other particles. So for their convention they have said that the particles which behave in this way, they are positively charged particles, and that is the other group is the negatively charged particles. So that's a convention, that's the way we have defined. That's all very fine, but you should not be satisfied with this explanation. Then charge is an inherent property, but this chargedness, I mean, whether it's a positive or negative charge, how fundamental is this property? Because you can add charges, right? Superposition of charges, you can add plus 2q minus 3q, you can add positive and negative charges. On the other hand, you also know that you can only add those quantities which are the same dimension. Now of course, the dimension of charge is coulomb. If it depends on what system you're working in, but whether a positive charge or a negative charge, charge is always, they have the same dimension. By dimension I mean that physics, the dimension of the term charge in an equation, that doesn't change. So you are okay, dimension is same. I understand charge, I can add charges, I can subtract charges, superposition. I No, you don't understand charge. You ask even more deep questions. I mean, what exactly differentiates positive? And I'm pretty sure that many of you have not even thought of these questions. But if you not think of these questions, you'll see that actually we understand very little of charge. Something which seems as simple as charge. Superficially, it's all very well, positive, negative. But how do we differentiate positive charge and negative charge? Then why cannot charges be fractional? Because at high school level, you don't know about quarks and all that. But the smallest amount of charge that can exist independently is an electron. That's the minus one. The charge is minus one in the electronic unit, minus one e, right? So why cannot I have a particle existing independently which has the charge, let's say, minus 0.7 e? Why not? Now to answer that question, you need to go very deep, and we also need quantum field theory and stuff. It's very complicated. Now, I'm not saying you start learning quantum field theory and ignore electrostatics in your high school. But if you develop this habit of asking questions, if you start with a single question, which might sound very stupid question also, but then if you go on asking why, you start with a simple question, then okay, why? You get an answer. Again, why this? You get again answer. Why that? Again an answer. So if you go down this loop of why, if you go down this path, after a certain point, after a certain number of whys, you will come to a dead end. I'm pretty sure you will. That is the thing. You start with any question in any branch of physics, not just electrostatics. After that, you keep on asking why. Then after a certain point, you will reach a point when you will be forced to say that I don't know the answer. I mean, it's an open question, it's a research question, nobody knows the answer. So if it's a very well known problem, maybe you will reach this level after asking why many number of times, or if it's already a very new and less understood problem, you will reach this level after asking why maybe two or three times or four times, less number of times. But you're bound to reach this because fundamentally our knowledge is incomplete, even about something as simple as basic as charge, electric charge. So this habit of asking why and keep on asking why. First of all, choose one question and go deep as you can go. When you reach that level, you write down that open question. After which you can proceed no longer, because if you proceed further, it would be philosophy and assumption. Science can only take you so far. Today, maybe of course in the future, our understanding will improve. That's the way it happens. Then you choose a different question, maybe in some different branch of physics, and you do the same thing. Why? Do the same thing. That is the way you develop your mind. You train your mind to think like a physicist, not solving problems. Solving problems is very important. I mean, not just from exam point of view. Even for a physicist, it's very important to solve problems because they give you a mathematical training. Not because they give you good marks in the exam. That is important for the system, but that's not really important to become a physicist. But if you solve a lot of problems, especially on your own, and then number one, you learn to deal with stress, because a physicist life is stressful. Maybe you don't have to give exams once you are a registered physicist and a qualified, but submitting papers, reviewing papers, doing taking care of all these duties, students, teaching students is a very stressful life. Solving a lot of textbook problems, especially the difficult ones, gives you a early training how to deal with stress. That's one plus point. One, apart from the exam part. So the other plus point is that it gives you mathematical training and some hands-on, like you know how to deal with problems. But still, that is not the most important. That's not even the that is not really what I mean. Everyone solves problems. The guys who go into competitive exams, they are also solving problems. So if you want to become a physicist, then you would need to do something different from the rest. That is, develop this habit of asking questions, this kind of questions. and maybe making a note of this maybe. And today you have YouTube, you have ChatGPT, you can make good use of it. I'm not, instead of generating reports using ChatGPT with copy pasting stuff and all, you ask ChatGPT this question: what is the charge? It will give you a very like basic textbook answer. Then you ask, no, but we don't fundamentally understand the charge. Why cannot there be a minus 0.7 each charge? If you ask this thought-provoking questions, actually ChatGPT will give you some very good answers in most cases. You can at least play with ChatGPT. You can have a discussion with it about these open questions, because and it's accessible to you. You don't have to email ChatGPT and wait for a reply after 7 days, and maybe you get no reply at all. So why not do that, right? That's the point. So ask questions, number one, and number two, or I should say within number one, ask questions from different branches of physics and try to connect them. Number one advice, and probably the most important advice if you want to become a physicist. And after doing all this, if you feel like no, this is not for me, then maybe you can consider a different path. Because you don't have to be a physicist. That's totally up to you. Okay, now I'll give you some one or two few more points I'll talk about and end this video. So, see, I was like initially, then like I said, it started with consciousness for me, and then I was into quantum mechanics, and then I explored quantum mechanics very deeply, like formulations of quantum mechanics and all. And I got interested in it very, and then I also explored a little bit of quantum field theory. I also worked on a project on theoretical HEP, high energy physics. And that slowly, I think, personally, I'm not saying I don't find that line of research interesting, but it's also true that it's become kind of saturated, because so many people are working on these problems, no progress so far. Because I think those questions are very interesting to think about, but if you want to make some real significant contribution to society, to science, there, I think it would be a better idea to work on problems like biological physics. We don't even understand how a single cell works. There are a lot of diseases in the human body, and biological physics is not just studying by the human body. You can look at biological systems. You can look at social systems, the dynamical systems theory. You can look at how humans behave, game theory, or some modeling, mathematical modeling, cellular automata, how structures form in nature, not just in the human body but in nature. The patterns forming when the birds are flying and flocking, information flow in living systems, transfer, lot of things you can do in this line. So nonlinear dynamical, using nonlinear dynamics and all this. There's a lot of scope in this line actually. And there's a lot of scope not only in terms of making some new discovery, but also contributing something real to society. Okay, so I think that's why I came to, and you can also retain the flavor of that fundamental questions in this line also. It's not that you are not doing quantum mechanics and quantum gravity, so you cannot talk about the fundamental nature of reality. Statistical mechanics is also a very, it's a theoretical, it's a branch of theoretical physics, and it starts with some assumptions like postulate of equal apriori probabilities and stuff. And if you think about statistical mechanics, the approach, not the applied statmech part which you are using to study systems and all complex systems, but if you think about the formulation of statistical mechanics, theoretically, a lot of, I mean, at least there's a lot of foundational, even philosophical questions here also, I think. Okay, and one thing is that, yeah, out of the box thinking is also very important. First of all, you can be good at many things. So that's why I did a lot of work in quantum mechanics, and in last 1 year only, this change came about, that I know I want to do nonlinear dynamics, statistical mechanics. And in this last 1 year alone, I have published two original reports, without like unsupervised reports, and very serious kind of reports. You can find them on ResearchGate also. One is on kind of a theoretical hypothesis on entropy and the arrow of time. That was a work in the intersection of quantum mechanics and statistical mechanics. The other is on emotional modeling emotions between two humans using nonlinear dynamics equations, a set of coupled nonlinear differential equations, and running simulations and all. And then I also did a project at an institute in India, IMSH Chennai, on synchronized oscillations and stuff. And I did a lot of, so all this stuff, doing all this stuff, I didn't find it very difficult. Of course, these are very basic level stuff. If I really want to do a PhD and stuff in nonlinear dynamics, it would be much more. But I didn't find that, okay, I've done quantum mechanics, so I didn't find the transition to be very difficult, because I loved statistical mechanics. I started loving StatMech, and I seriously came to know about StatMech only in the last year, in my last year of my BSc. Before that, I only had a very vague idea of what StatMech is all about. So if you're really interested in it, you don't really like, oh, no, I have done quantum, so I have to stick to quantum. I cannot go do it. So, no, why? And also, since I've done quantum very rigorously, it has trained my mind to think in a way that I didn't find it very difficult to learn StatMech. So if you're very good in one branch of physics, very good in it, then even if that may not be very much relevant to your current branch, since you are good in that branch, you have this habit of thinking deeply and learning of yourself. So that habit will help you even if you shift branches. That is the thing. That is the point. Okay. So, and I think physics is everywhere. I mean, if you're studying biological systems, then does it mean that general theory of relativity doesn't hold? Of course, it holds. Gravity is not very significant between cells or molecules. That's why we don't care about gravity. These people who are studying biological systems, we don't care about Einstein's field equations. We are more into the electromagnetic interactions, what is happening, the free energy minimization, entropy maximization, what is happening to the energy and entropy, how the system is evolving, what patterns are forming, what is happening to the like how they're self-organizing themselves so that it's the equilibrium state, how so much of charge is packed in so little volume. We are more interested in this kind of stuff. We are not really interested in gravity. But does that mean that gravity is not present in the system? Of course, they're present. They don't have an effect that can alter the behavior of the system. So we ignore it. But Einstein's equations are as valid for a cell as it's for a astronomical body. Getting my point? The people who are doing astrophysics, they don't really worry too much about the quantum effects. But does it mean the quantum mechanics doesn't hold for a large macroscopic bodies? Of course it does. Again, when it comes to quantum mechanics, decoherence and all the quantum measurement problems, a very subtle topic, a very less understood topic also, I would say, even after 100 years of quantum mechanics. But yeah. Now, I mean, so you should have the big picture that what am I working on, what are the limitations, what are my assumptions, and what is the scale I am looking at. So I will be focusing on that, but that doesn't mean that the other physics is not valid here. Okay, and you should try to ask out of the box questions so that you can do something. Millions of people are exploring biological systems, but if you want to make some really new contributions, you should think about biological systems in a different way. First of all, a formal training is required, an institutional training, a degree that is required, not just for your as a gate pass to BSc is not just a gate pass to MSc. BSc is also required because some concepts you learn and it gives you an overview of all the branches of physics. From MSc you can specialize. That's fine. You don't need to wait to PhD, but at least BSc level you should have a good knowledge in everything. So like I don't judge people based on their CGPA in their exams and bachelors. I know that, but still I think CGPA is important. At least you should have a decent CGPA because if you don't have a decent CGPA, that means you don't have a basic comprehensive knowledge about physics. Maybe you know a lot about one particular branch, could be the case, but that is also important to some extent. You don't need to be a topper, but yeah. Now you should always think out of the box, and it's very important that you should always be aware of the limitations of your model and what assumptions you're working under. Don't get too lost in your theory that you forget the assumptions, the big picture. You may work on biological system, that doesn't mean you can ignore the universe, or you may work on the universe, that doesn't mean you can ignore what is happening here, because black hole information paradox, we have this entanglement entropy versus this curve, this page curve versus time curve. It actually this shows the relation between entropy and information, and in a way we see similar things even in biological systems, any system for that matter. It's a lot. There are a lot of other examples also where we have seen phase diagrams about black holes and a similar behavior in superconductors and semiconductors and in condensed matter physics also. So yeah, out of the box thinking. Let me give a simple example. If I ask you how many different ways you can write 3 as a sum, not subtraction, uh, you will say 0 plus 3 is 3, 1 plus 2 is 3, 1 plus 1 plus 1 is 3. Is there any other possibility? I have said not subtraction. So 4 minus 1 is 3, 5 minus 2 is 3, 6 minus 3 is 3. You cannot do that. You can go on, but no subtraction, only addition. You will say, no, then there are only 3 possibilities. You have already said all of this. 1 plus 1 plus 1 is 3, 2 plus 1 is 3, and 3 plus 0 is 3. So this is the many people will fall into this trap. But I have never said that it should be an integer. Half plus half plus half plus half plus half plus half is also 3. All I said is it should be a sum. You can also sum fractions. I never said it must be a sum of integers. So 1 by 2 into 6. I mean, if you sum 1 by 2 6 times, that is also 3. 6 by 2 is 3. 3 by 2 plus 3 by 2. Two fractions. Sum them up, what you will get? 3. So there are a lot of ways you can write 3. Using a sum, no subtraction. But you have to think that's what I'm saying. Sometimes people we lose the big picture. I'm like, no, I have covered everything, but we forget our this assumption that we are dealing with only integers. This is an assumption. I never said integers. right? It's a very good example. Of course, in dealing with real complex systems and that physicists deal with, it's much more difficult. It's not as simple as this, but I think I just give an analogy, an illustration kind of thing. Last example, last advice before I show you something, and then I'll be done with this video. Last advice to you would be, you know, yes, don't generalize humans as good or bad. This is a general life advice, you could say. It's not just if you want, whether you want to be a physicist or not. If you want to be a physicist, my advice to you would be start exploring everything in physics at a basic level. If you're a high school student, don't need to go very advanced. But YouTube, prefer YouTube over popular science books and good YouTube channels. Expose yourself to a lot of perspectives, not just one particular perspective. And ask this why. Ask these questions. Start with a question and go deep, as deep as you can go until you reach an unanswerable question. Advice number one. Advice number two, reach out to people in the field. You can today there is an internet. You open the website of any good university where the faculty, one of the faculties may be doing a work on working on a problem that you find interesting. Email him or her. This trouble, this pain you have to take. You have to email, maybe you have to email 100 professors. Maybe 99 of them will not reply. Even if one replies, you might form a very lifelong connection, which might turn out to be very important in your career if you decide to explore physics. What you will email? Just email that I am a high school student from this country, and I am really interested in physics. I have these ideas, but I was wondering, and I'm very much inspired by your work, the kind of work you're doing. Although I don't understand all the technicalities, but I saw on the website. So if you could share some advice with me, that because often they will be a much better person. So that is also one advice to you, that reach out to people in the field, and they need not always be senior professors, because senior professors usually don't have enough time to reply to emails, especially emails like this. They already have a lot on their plates. You could also reach to PhD students, postdoc students, because they are doing a PhD, so they are not very old than you. I mean, the age gap, the generation gap is not so much. They have also gone through your phase, high school or undergraduate, maybe a few years back, so they will be able to give a much better, much honest, much useful advice, much useful information, much useful guidance. And often PhD students, they have maybe they can relate with your pain a better, because maybe they were also questioning that whether I should do a physics or not. So you can reach out to them. In most university, most institute website, if you go, you can get the emails of all the doctoral students, or at least the postdoctoral students. You can reach out to them also. Advice number three, and this is a general advice, not just for physics, is that you should not generalize. Humans. Okay, okay. If you behave in a good way with humans, I said this in a lot of my videos. They will also behave a good in a positive way with you. But that doesn't mean they're your friend. I mean, don't judge humans too quickly. Nobody is your friend. Nobody is your enemy. Also, I'm not saying just assume everyone is your enemy and behave badly, or just isolate yourself. That is also an assumption. And science, in science, our we always try to remove the assumptions, or at least build a theory that gives the correct results and makes the correct predictions with as little assumptions as possible. It's not always possible to have a theory with no assumptions at all, but as little assumptions as possible. Okay, or always, often we try to connect assumptions, so to show that okay, these two assumptions actually can be reduced to a single assumption. So no assumptions. Don't assume that somebody is your friend just because they were with you when you were feeling down. Maybe they were just pretending, or maybe they had some unscrupulous purposes. They had something to gain from you. And if somebody was not beside you when you were down, that doesn't mean automatically they're enemy, because maybe they didn't understand your problem. Maybe they were going through something worse. So you don't assume someone to either be your friend or enemy. Not required at all. You will not behave in a bad way with anyone, but you will again not get overly close or attached with anyone. You will always maintain your distance and maintain your individuality, because we humans, we often have a tendency of generalizing stuff, not only when it comes to other people, but also I my experiences have been like this, so I will just quickly generalize this, that okay, that people is behaving that way. So no, everybody is different, everybody has their own problems. You should not and you cannot generalize. If you do, then that will be a biased, you will get the wrong results, you will take the wrong decisions if you do that. Don't generalize, don't take decisions, don't form conclusions. Maintain a distance, but don't act hostile, and just let things evolve on their own, and take decisions accordingly. Don't make any unfounded assumptions. Very important advice. And finally, see, one important advice would also be, you should, I mean, see physics not just as a means to make a make money if you want to be a really, really good physicist at least. That's what I think, personal view. You should also see it as something of a, I mean, you should be passionate about it. You should find meaning in your work, because physics is a very long and difficult path. PhD, postdoc, or maybe if you go get a good institute, especially outside India or in it, you can get good money also. Financially also, you maybe well, even but even then, academia is very much competitive, and if you don't love what you do, then physics may turn out to be very frustrating, very challenging, very kind of thing. So ensure that you love what you do, but not just as a means of livelihood, but you actually love what you do. You love thinking about these questions. Only then, otherwise, physics may not be the right path for you. And by love what you do, I don't mean you should always be just passionate about physics. You should also do some real work. You should strive to work more than your peers. By peers, I mean, okay, maybe you are doing an undergraduate course in physics, so you're already with a group of people, all of whom, at least most of whom, like physics, or at least they have chosen physics. So then, but even among them, you need to stand out somehow. You should try to stand out at least. You know, and by that I'm not saying do 1,000 of internships. Internships are nothing. In my experience, I've done some internships and I know what students have done. I used to think that doing an internship under a professor in a good institute, it means you are doing some real research. Oh my god, that's very impressive. When I was in school, I used to think, but after having done two internships at prestigious institutes, funded fellowships myself, and having looked at my friends, the kind of internships they're doing, the kind of reports they're making, in my case, I would say my guides, supervisors in both the cases are very good, and I try to do very original work. But in most cases, at least in India, it's not the case. Internships don't define anything. Anybody can do that. It's easier than exams also, in a way. Totally guided kind of thing, and you just take some data and do something, and just somehow write a 12-page report, and you get a certificate, and you brag about it. I did an internship in IIT, and then I did an internship in whatever institute it is. It doesn't really matter. Some people really do good internships, but I think that cannot be a benchmark. That's what I'm saying. Or that cannot be a yardstick, at least. Not a general yardstick, at least. Not in my experience, at least. But try to think, and not just thinking, try to jot down your questions, and if possible, explore those questions on ChatGPT, on YouTube, and maybe write a report on it. Don't use ChatGPT to write the report, but you can explore the stuff. You can ask ChatGPT that tell me something about whether some research has already been done in this area. You type your question, and ask ChatGPT to give you references. It can do that. This is how you can use ChatGPT to your benefit, not use it for these things like you're generating a report and all the copyright, and no, not that kind of thing. You could also manually search the internet whether there are papers about this, whether already some prior work has been done on this topic. But ChatGPT can do it much quicker for you, and there is no you are not doing anything wrong ethically, or if you just use ChatGPT for this. That's what I'm saying. And try to write reports by yourself also. No, not always not to do an official internship. That's what I have been doing. So this is also very important advice. You should be passionate about it to such an extent that you have to start writing your own reports, own hypotheses. Maybe there's some of the first one of them will be very poorly written, very wrong, even wrong. Don't get discouraged. You are a high school or an undergraduate student. Nobody expects you to write a research paper at this age, but still you're doing something that your friends are not doing. So you should feel proud about it. It won't be like an overnight success. Of course, because at the end of the day, you will be remembered for your works, not your relationships with other people. Maybe your friends will mock you. That guy is not just writing a report. This is not serious about exams. You have to face it if you want to do something different. Now I want to show you something. Okay, so this is a paper. I think you can see my screen now. This is a paper, one of the papers, independent reports I wrote in the last 2 months. May now I will give this is published on my ResearchGate, and it's also freely available. The preprint on, I think, on Zenode also. I uploaded it to Zenode also on my all my research profiles. You can find. I'll give the link in the description as well of this video if you want to read. It's a very long report, by the way, 86 pages. Now, basically, it's a kind of hypothesis, but the hypothesis is only a small part. Initially I have just introduced. This introduction is kind of a literature review of known topics, but I've done it in a very succinct as well as a very rigorous manner. I think you will, if you're into this thing, and you want a very light reading, not very technical, you can read this article. Here I've explored the quantum uncertainty, the entropy in StatMech, and information out of time. Now the reason I'm showing this to you is that I want to ask you a question. Okay, wait, give me a second. All of this is fine. I don't these things I don't want to discuss right now. You can read this article. Actually, it's a very, I think it will might be helpful to you, of course. Okay, I'll not go into my hypothesis or any technical details of this article in this video. But yeah, my question is okay. Now, if you are familiar with statistical mechanics, just even just the basics, only then you listen to this part. Otherwise, you can just skip the next few minutes because otherwise this may not make sense to you, and it's not possible for me to explain these things from scratch in this video. Sorry. Yeah. The reason is fundamental assumption in StatMech is that every possible micro. So basically, a system in equilibrium, uh, overall, there may be a macro state of the system. Let me give you a simple example. By show you a simple picture actually. Suppose we are looking at a system and these are four possible configurations. Now all of these four they are the same macro state. Macro means macroscopically. Suppose we assume that you cannot distinguish these colors. These colors have been shown just to for ease of understanding. But just assume that you cannot distinguish the colors experimentally. You don't have a device in a laboratory by which you can distinguish the colors. So then from a large viewpoint, from a macroscopic point of view, all of these four pictures are equivalent. Equivalent because you have three balls in the left partition and only one ball in the right partition in all four cases. So the same macro state. But microscopically they are different because here the red ball is in the right partition, the other three in the left. Here it's a green, here blue, here yellow. So they're microscopically different. So they're the four microstates corresponding to the same macrostate. Now a system can be in many different microstates. Like if you have a box of gas made up of millions of gas particles, so all of these gas particles are moving about, jiggling about, so they can be in different microstates, but yet they can correspond to the same macrostate. Now depends on what macroscopic parameter we are measuring, that is important. So say we are measuring temperature, so it's totally possible that you are measuring temperature, okay, so it's totally possible that there are many possible microstates which can correspond to the same temperature because temperature is a macroscopic quantity. It depends on the average behavior of all the gas molecules. So even if we have if you have a configuration where there are millions of molecules, so even if you interchange some of these molecules, the overall macroscopic temperature will not change. So the same macrostate. Okay, this part is very important. Now, what I would like to discuss is that yeah. So in statistical mechanics, we start with this postulate. It's a kind of assumption. It's a very valid assumption also in most cases, is that if a system in a given macro state has, let's say, just for the sake of argument, let's say it has only four possible microstates. The picture I showed you, four microstates correspond to the same macrostate. Then over time, all the four microstates would be are equally likely for a system in equilibrium. Equilibrium because if the system is not in equilibrium, then there is some heat flow, information flow from within the system and its surroundings. So then the things will be more complicated. Then the external conditions might change the probability. But otherwise, the system in equilibrium, if there are four possible microstates corresponding to the given macrostate, and let's say the system is in that given macrostate, then all these four microstates will be equally likely over time. That means, let's say I analyze the system, I study the system for 1 hour, and the system is in this macrostate for this entire duration of 1 hour, and there are four possible microscopic configurations. There are four possible microstates that correspond to the same macrostate, even though I cannot measure the microstates. Then, on average, for 15 minutes, I would see microstate 1, for 15 minutes, microstate 2, for 15 minutes, microstate 3, for 15 minutes, microstate 4. Because there are four microstates and all of them are equally likely. So, 1 hour divided by 4, 60 minutes divided by 4 is 15 minutes. So, they will get 15 minutes each. No, I don't mean it's a continuous 15 minutes. I'm not saying that it will be in the microstate A for the first 15 minutes, microstate B for the second half, then third or fourth quarter. No, not that. It could randomly fluctuate between microstate A, microstate B, C, D, A, B, C, D, A, B, D, 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 C, B, A, B, random sequence. But over this entire time period of 1 hour, if you analyze it, then you'll see more or less the probability is equal, 1 by 4, 1 by 4, 1 by 4, 1 by 4. That is what I mean. Okay, so fundamentally we cannot assume a particular microstate to be more probable than any other microstate without precisely explaining this preference. If you assume that no, microstate A is for 30 minutes, but the other microstate is for 15 minutes, and the other two they are 10 minutes and 5 minutes, then why this particular division of time? You cannot explain that fundamentally because it's a system in equilibrium. You don't have any other disturbance or any other thing. So we do not expect to see any particular possibility being preferred over any other possibility at a fundamental level. Okay, this part is You may not, the context may not be. I'm just skipping this now. In statistical mechanics, we have two extremely fundamental ideas that we will now briefly discuss: ergodicity and the PEEP. This is called PEEP. PEAP. Postulate of equal a priori probabilities. A priori is A, and then P probabilities. So these two things are actually, one implies the other, but this connection is not usually taught in class. Now I am discussing this because I want to give an example when I say connect the dots. Suppose you are learning statistical mechanics in college in undergraduate, and your teacher tells you the statement of ergodic hypothesis and this postulate. You have to think yourself that can I connect them. Now you actually can. Let me tell you how. Although this connection is a bit involved. Okay, not really involved, not really difficult, but it's usually not discussed properly at least at an undergraduate level, at least in my experience. So the ergodic hypothesis tells you that the time average of a macroscopic parameter of a system must equal the ensemble average. Maybe you didn't get anything, but let me give you an example. Suppose we want to measure a macroscopic parameter A. A could be temperature, A could be pressure, anything, any parameter of a box of gas in equilibrium. So let's construct a hypothetical scenario in which we measure A for this system a large number of times and at infinitesimal intervals. So let's say we want to measure the temperature of a box of gas. So we measure it right now. In the next second we measure it, and then in the next second, and we do this for a long period of time. I mean theoretically for an infinite amount of time. Suppose, and then I get an infinite number of, I get a large number of values for each of these measurements, and let's say I measure it n number of times, where n should be a very large number. I mean, it tends to infinity, not really infinity, but tends to infinity. So then if I take the sum of all these values and divide by n, that's how we calculate the average, right? So then that is the average of these values. Then that will be the time average. Why time average? Because all these values have been taken for the same system in the same macro state, but for different amounts of time. So this is the time average, right? I think you get my point. Now let's consider another hypothetical picture in which we create a very large number of identical copies, which we call an ensemble in technical language, now of the system in space. Now let's say we have a box of gas. Suppose we buy some magic, just a thought experiment. We duplicate this box and we get two boxes. Then we duplicate again, and like this we create a large number of copies, n number of copies, where again ideally n tends to infinity. A large number of copies of this box in space, different copies, physical different copies, but of the same box. But the same box of gas means the same, identical copies means identical in what respect? They are in the same macro state. The macroscopic parameter is not changing. Suppose you're measuring temperature, temperature is the same for all of these boxes. Micro states may be different, you cannot measure that. So when we say identical copies, we mean all these copies must be in the same macro state. As we have already discussed, there can be many possible microstates corresponding to the same macro state. So all these identical copies of our system are allowed to be in different microstates as long as they correspond to the same macrostate. Now imagine we measure the parameter A of all these copies of the system at once, because now there are a lot of copies in space. So you can technically measure them at the same time. I mean, of course, if there are maybe 1,000 box of gases, one person cannot make a simultaneous measurement in 1,000 systems just at this same instant of time. But I mean, in principle, the thought experiment is like you can measure all of this parameter A, this macroscopic parameter A, for all these boxes at the same time. Take a snapshot at the same time because they are in space. Okay, and then you take the average again, and this will I think give you the yeah. So this will give you the ensemble average. Okay. Now the ergodic hypothesis tells that the ensemble average and the time average are equal, which makes sense. Okay, I am measuring a parameter of a system, so whether I measure this same parameter over a large number of times, I mean over a long period of time, many times, or if I just make a copy in space, make many copies in space and measure it, I should get the same value because I'm taking when I take the average. Kind of makes sense intuitively, but let's understand this much more deeply. Yeah. Now, the first question which you may ask is very valid question. If you have followed this argument, I told you that you cannot measure the microstates, and I also told you that when we are making these copies, identical copies, ensemble, all the copies are in the same macro state, and you can only measure the macro state, macroscopic parameter. So then you should get the same value A for all the boxes. So what is the point in measuring a 1,000 times and dividing and adding them and dividing by 1,000? 1,000 A over 1,000 is A. So we already know we will get A. We cannot differentiate microscopically. So what is the point of all this? You might form this question. It's an important question, but let me tell you the answer why this question is not entirely correct. So imagine we measure, I told you, yeah. So imagine we measure the parameter A of all these copies of the system at once and calculate the average. This gives the ensemble average. Now, according to ergodic hypothesis, both these average values, the time and the ensemble averages, should be equal. Now, one might wonder what is even the need of considering an ensemble average, since we have said that all the identical copies of the same macro state and we are measuring a macroscopic parameter A. So, should all these identical copies not have the same value of A? It is important to realize that certain macroscopic parameters of a system are functions of the underlying microstate and can vary across microstates corresponding to a macrostate that is defined using some other macroscopic. Okay. Consider this example. Ensemble averaging is important in general, of course, and that is because when we are measuring, let's say we are measuring, we have a box of gas where the energy is fixed. It depends. You can have a box of gas where the energy is fixed. That means, yeah, temperature is also kind of fixed, because at least according to classical statistical mechanics, the kinetic energy of the gas, if you consider the gases to be free particles, no potential, then the kinetic energy is just related to the temperature. So there are many possible microstates corresponding to this same energy macrostate. But suppose, let's say the energy is fixed. That is how the system is given to me. I cannot change that. But let's say suppose we are interested in measuring the pressure. Now in this case, the pressure of the system will be different for these different microstates. You can distinguish the pressure, even if the energy is same. So in some microstates, the particles will be colliding with the walls of the box more frequently. In some other microstates, the particles will be colliding among themselves in the middle of the box more frequently, and so on. But overall, the amount of temperature and energy is remain the same. That is possible. So in this case, you see the pressure will be different for each microstate, and the average pressure can be determined by averaging the pressure measurement outcomes obtained for each microstate. I think you get the idea. Now I will tell you why ergodicity and this postulate of equal apriori probabilities, they are related. Just via logical arguments, no mathematics or anything. Now let us think about the implications of the apparently obvious sounding claim that the time and ensemble averages must be equal. So when we consider the identical copies or ensemble, we take into account all the possible unit microstates. Why all the possible? Because we have considered an infinite number of copies. I mean almost infinite. N number of copies where n tends to infinity. So if I duplicate this box infinite number of times, all the microstates will be more or less covered, right? So imagine all the possible combinations of position and momentum of all the macroscopic gas molecules in a box of gas made up of a large number of molecules. It's a huge number. This means in this ensemble we have one copy of each macrostate corresponding to the given macrostate, because we have taken an infinite number of copies, identical copies. The ensemble average thus is the average of all the values obtained for each microstate counted only once. Why only once? This argument is a bit difficult to follow, might be a bit difficult to follow. See, very loosely speaking, we consider an almost infinite number of copies, identical copies, and there are an infinite number of microstates, because so many gas molecules and so many possible combinations of position and momenta. So it's a huge number. So infinity. So we can expect, very loosely speaking, that there will be a one-to-one correspondence. That each identical copy in the ensemble will correspond to one unique microstate only once, counted only once. When we're making a large and almost infinite number of measurements at very small intervals of time, now I'm talking the time average, we get the same result, because this means as a system evolves. See, this is the ergodic hypothesis claims. We don't yet know why this should be true, but this claim is actually indirectly leads you to the postulate of equal apriori probabilities. For the ensemble average, okay, you understand that, okay, we are taking almost an infinite number of copies of the system, and the system has an almost an infinite number of microstates, so there should be, for each copy we are counting the microstate only once. We have one copy of each microstate corresponding to the given microstate. See, read this carefully. When we consider the identical copies of the system, we take into account all the possible unique microstates of the system. That's why I said we should take a large number of copies. This number is very large, infinite for all practical purposes. Imagine all the possible combinations of position and momenta of all the microscopic gas molecules in a box of gas made of larger molecules. So that is what I mean by all the possible microstates, all the possible combinations of position and momenta. This is also a huge number. So that basically in the ensemble we have one copy of each microstate corresponding to the given microstate. Right. Now, so we have only one copy of each microstate, because otherwise, what is the point? That is how we define ensemble in statistical mechanics. Why should we count one microstate more than once? So that is why this ensemble average is the average of all the values obtained for each microstate counted only once. Now we are seeing, I mean, now the ergodic hypothesis or ergodicity is making a claim. It says that, okay, this is fine, But when you make a large number of, almost an infinite number of measurements at very small intervals of time, then also you should get the same result. This is what ergodic hypothesis is telling you. So this means that as the system evolves over a sufficiently long period of time, it accesses all the possible unique microstates. Unique is a very important term here that correspond to the given microstate. And importantly, the system will never revisit a microstate it has already visited without first covering all the available microstates. Otherwise, these two numbers would not be the same. In ensemble, you have one microstate only once, no repetition. And the ensemble average is equal to the time average according to ergodic hypothesis. So that means even if when the particle is evolving in time over a large period of time, long period of time you're measuring, the particle will first cover all the microstates. You visit each microstate only once, and cover everything. Then maybe it will revisit. But it will not visit the same microstate twice if some microstates are totally unexplored. That is what I mean. So consider the number of microstates to be infinite. This implies that it is equally likely to find a system in equilibrium in any one of the possible microstates that correspond to the given microstate. Because it's equally likely because over a large number of time, and since the microstate is infinite, so over a large number of time the particle will visit every microstate only once. If the time was finite, then after the time interval, after covering all the microstates, the particle will again revisit. But it's for an infinite amount of time, infinite number of microstates. So number of microstates is infinite. So that means the particle will visit. The system will visit each microstate only once, because the ergodic hypothesis already tells you that the time and ensemble averages are equal. So they're equal means that all the possible microstates are equally likely. Because if it was not equally likely, then maybe the particle does not visit the microstate at all, or maybe the particle visit a microstate more than once. It's not so, and equally likely, and that is in fact the statement of this PEEP, postulate of equal a priori. So they're related. I mean, it's kind of obvious. See, if you have I think I gave this example some. Mm, all of this is okay. This is a simple example. Let me just skip this portion. So simply put, if we have 10 single rooms in a guest house and 9 guests, we would allocate 9 unique rooms to the guests and certainly not force 2 of them into the same room. So until and unless all the 10 rooms have been explored, we will not come back to the same room, to our previously explored room. So the same way, if we imagine each point in the whatever, I mean, this is the example I was trying to say. Now I would also like to discuss this. Okay. So this is a talk given by Professor. Just a second. This is a talk given by Professor N.D. Haridas. He is a retired professor of the Institute of Mathematical Sciences, Chennai, and I had the great fortune of discussing, having an interaction with him, and discussing some stuff with him over the last few. This is actually a summer school on quantum foundations, which was organized by Bhaktivedanta Institute, Kolkata, and SIDAC Patna, Center for Development of Advanced Computation, Patna, and this was like this summer school was you see, summer school 6 to 8 June 2020, Kolkata. I myself also gave a talk in the summer school. You can check it out if you want. I'll give the link in the description maybe. So I got to interact with a lot of physicists in this talk. You know, but I loved the Dr. Professor Haridas's talk because it's a very logical talk without using a lot of technical jargon. He exposed a very fundamental limitation in our understanding of quantum mechanics, and I really liked the way he presented his topic, that quantum superposition principle is all of quantum theory. And the reason I'm showing this to you in this video is that this will give an idea, I think, about how to learn physics and how, especially if you want to become a physicist. You know, so okay, let's just basically argues that quantum superposition principle is, we all know this basic definition, but why is it very much different from classical superposition principle is something which is not very much explored in textbooks and all, and why quantum superposition principle is the most fundamental and maybe the only defining feature of quantum mechanics. It's a very interesting argument. Okay. So this is Dirac's definition of superposition principle. So if A is a quantum superposition of two or more states, in quantum mechanics we basically make measurements on a particle and make measurement on the states of the particle. So let's say we have a particle or a system which can be in two states B and C, and A is a superposition of those states, suppose. So then according to Dirac, then every outcome of any measurement on A on the superposition state must also be a possible outcome of the same measurement on at least one of B or C. If we consider only two cases, B and C, then one of B and C. So understand this very clearly, what Dirac is trying to say. If A is a quantum superposition of two or more states, let's say if A is a quantum superposition of two states B and C, then every outcome on any measurement on A must also be a possible outcome of at least one of B and C. Because otherwise, what will happen? Suppose A is a superposition of B and C. So on measuring B, I get outcome, let's say X. On measuring C, I get outcome Y. Now A is a superposition state of the states B and C. Then on measuring A, I can get many outcomes on measuring A, but all of those outcomes must be a possible outcome of must be either X or Y in this case. I mean, I mean, it must be a possible outcome of the same measurement on at least one of B and C. Of course, this is very important. The same measurement. What we are measuring, position, velocity, momentum, that is important. I'm making a position measurement on B and C, and I'm making a velocity measurement on A. I cannot expect this principle to be true. But if I make the same measurement and I get, suppose for B I get X outcome, for C I get outcome Y, and then I make the same measurement on A, which is the superposition of B and C, then what I will expect is that whatever outcome I will get, it will be like, it will also be a possible outcome of the same measurement on at least one of B and C. And see, this is the Hilbert space formulation, usually what we're taught in standard quantum mechanics textbook, the textbook way, that this psi is a superposed state. This is the bracket notation. The psi, the wave function, it's a vector in the Hilbert space. This kind of thing, right? It's actually a ray in the Hilbert space, but whatever. For I don't want to go to the technicalities. It's a vector in the Hilbert space. Even that is not an accurate statement. It's a particular type of vector space, and how this formulation came about, it's very mathematical actually. Like why vector space, the basis, how to define the basis of the vector space, what are the bases represent, the state vectors, the bracket notation, and all this stuff. You know, the normalization condition and all, orthonormal, there must be orthonormal basis. And then we finally get to this inner product space. Okay, but basically here we have a state chi1, we have a state chi2, then any state psi, which is a linear superposition of these two states chi1 and chi2. So then suppose linear superposition means with this kind of thing, general representation of a linear superposition, alpha chi1 plus beta chi2. Entire formulation of quantum mechanics is based on linear algebra. So then mod alpha square plus mod beta square has to be 1, because mod alpha square is a probability corresponding to this, and beta square is a probability corresponding to this chi2. So the total probability must be 1. And this Hilbert space formulation is actually compatible with Dirac's statement. Dirac says that any measurement on A, that means any measurement on psi, must also be a possible outcome of the same measurement on at least one of B and C. That means at least one of chi1 and chi2. That means if this was not true, suppose there is no requirement that it should be a possible outcome of at least one of chi1 and chi2. That means alpha and beta both could be 0 if this was not true. But if both are 0, then alpha square mod alpha square plus mod beta square would be 0, would not be 1. But the total probability is always 1. We know that's a fundamental constraint in probability theory. The total probability of all the possible outcomes has to be 1. So I think you can see the equivalence. At least 1, because okay, let's say alpha is 0, but then beta would have to be 1. I mean, that is still allowed. Or both. Okay, so now why is this fundamental, this Dirac's formulation is very fundamental, because it's even if this Hilbert space formulation is not adequate for some situations, for some scenarios, then also this is a much more general argument, kind of, if I put it very, it's a very, this talk by Professor Haridas was a very interesting talk. And although at first glance it may appear simple, but even I didn't understand all of it, like it takes time to understand. Just a second. Yes. Okay, so I don't know, it's still buffering. Give me a second, please. Okay, so yeah, now yes. So what I was telling to you, I already told this. Now this is some very important. See, okay, I think I can skip all this, because I'll give the link of this talk. You can listen to the entire talk. I think you should, if you're interested in these topics. You can listen to the entire talk. I will not go through the entire talk because this is not my talk. Okay, but I'll just give you some basic outline some important features of quantum superposition from this talk, because this is not usually how quantum mechanics is taught in colleges, but this is how it should be. So at least you can get some idea about how what I mean by thinking out of the box and that kind of stuff. The advice I gave through the video. So the superposition principle, that this is a very important to realize, because this is not very much emphasized, but it should be, that the superposition that occurs in quantum mechanics is of a very different nature, fundamentally different nature from the classical superposition. So although we use analogy, because mathematically, okay, the classical waves are also subject to the linear superposition principle. Like if A is a solution to the classical wave equation and B is a solution, then any linear superposition of A and B, like let's say alpha A plus beta B, that is also a solution. That holds both for the classical wave equation as well as Schrodinger wave equation in quantum mechanics. But the types of superposition we're talking about, like classical superposition and quantum superposition, they're fundamentally different, which we need to understand. And we can actually build up the theory of quantum mechanics on the basis of this superposition principle, actually. That's why it's essentially almost all of quantum mechanics is superposition. And the fundamental difference is that quantum superposition involves physical states, but not classical superposition. Classical superposition involves, okay, electromagnetic wave. Now, electromagnetic wave is not a physical state. Yeah, it's just a formulation. Electric, but that is important thing. But what you're actually measuring there is an electric field. You are not measuring the electromagnetic wave amplitude or something. You're measuring the electric field. And electric field is something you can measure. You can have some value of the electric field, some definite value. Quantum mechanics. Okay, can you really measure the wave function? See, let me tell you. Let me show you the argument. It's a very important argument, actually. Okay, give me a second. Okay, so classical superposition principle. Let's say we have electric field plus E and electric field minus E at the same point. So this after superposition, the total electric field will be zero. That's very fine. Now the possible values are plus E, minus E, and zero, and they are all allowed values and measurable values. But this does not satisfy the Dirac's condition for superposition. Yeah, Dirac's characterization of states is satisfied. Okay, so they are observables and they are all allowed and measurable. But what did Dirac say? Let's go back. What did Dirac say? Dirac said that if A is a quantum superposition of two or more states, let's say B and C, then any measurement on A, every outcome must also be a possible outcome of the same measurement on at least one of B. Basically, this is the statement, right? So basically, in this case, what we have, let me show you. Yeah. So B, let's say the state B is plus E and the state C is minus E, and the superposition state A is zero. So if the state A is zero, then if a measurement on A will always give you zero. But zero is not neither plus E nor minus E are zero. So this superposition is not being satisfied. I mean, Dirac's condition for superposition is not being satisfied. Get the idea, right? So basically, in case of quantum superposition, see, let's say we have it's a superposition of two states that Sz is could be 1 or minus 1. These are two states of Sz, and we're taking the superposition of them, a linear combination, or 1 over root 2 Sz, this state, one state, plus 1 over root 2 minus one state. And then we're getting the along x we're getting one. Now these notations might be very confusing to you if you have not already learned quantum mechanics. This is all just I'll not go deep into this, but basically, uh, unlike in the classical situation, Sz equal to 0 does not correspond to a quantum state of the system, but the outcomes are always plus minus 1, and here you cannot predict whether the outcome will be plus 1 or minus 1 for each measurement. Can be either plus 1 or minus 1, but not both. So we need a probability interpretation to make sense of this. In the classical case, it was not that. See, here Dirac's condition is being satisfied, that the superposition state is also 1 and A is also 1 and B and C are 1 and minus 1. So any measurement of A will give you 1, and at least one of them. Okay, so yeah, here we have also a 1. So it's being satisfied, right? I think we get the idea. Definitely you should listen to this talk. It's a very I'll give the link in the description. But anyway, so the outcomes of commuting, non-commutativity, discrete observables and stuff. These are the very little bit technical, and especially don't want to discuss this in this video. It's not the main point. Maybe I'll make a video about this in the future. Don't worry. And what? Yeah, this is the very important. This is the very important slide. Very important slide in Professor Haridas's talk. I had a very great discussion with him also about a lot of stuff. Actually, he's a very probably one of the greatest minds I've met lately so far. I was very much impressed. Anyway, so what he's saying is that, okay, so this is the psi is a wave function, and you have this as superposition. So if psi 1 is a solution to Schrodinger's equation and psi 2 is also a solution, then a linear combination of psi 1 and psi 2, let's say alpha psi 1 plus beta psi 2 is also a solution. Let's say this is psi, this is also a solution. That's a linear, that is the superposition principle, basically the mathematical statement at least. But yeah, thing is that this looks the same as if we just write E in place of psi, E1 into this, so it looks the same as the classical superposition principle. But point is, see, if let's say if we could, the electric field is something we can measure, but wave function is something we cannot measure. It's an abstract mathematical quantity we have constructed to study quantum, the formulate quantum mechanics, but we cannot actually measure the wave function. We needed the probability interpretation, the Bond rule, the mod chi square. Mod chi square came later, but anyway, we needed an interpretation. Wave function by itself has no physical interpretation. People tried, of course. Schrodinger himself tried a fourth order Schrodinger equation actually, to make things, but it didn't work out. So Schrodinger equation is actually complex, imaginary. Although the outcome of any quantum measurement cannot be imaginary, it has to be real. Any outcome of any physical measurement must be real. Whether it's you're doing a measurement on a physical system, the outcome has to be a real number. Whether your equation is complex, whatever. Schrodinger equation is complex. We have a I in the equation, right? I h bar. I is an imaginary number. That is the thing. So why couldn't we have repeated the same arguments that we do in classical superposition and here too, and that will be no issues with measurements. Most importantly, no probabilistic interpretation would be necessary. The point is that if quantum mechanics could be measured, then we do not need the quantum superposition principle, different from classical superposition. That means from here we can say that quantum wave functions cannot be, they are not measurable, unlike classical electric fields or these things, right? That is the way the argument goes. It's very unorthodox, not unorthodox. Is Dirac actually mentioned this in his book also, but this is usually not very much explored in textbooks. That's why I'm saying it's very important to think like this. Because basically, okay, all of this I'm just skipping, but basically the point is, yeah, it's actually unnecessary to think in terms of waves, particles that do, because it's a very confusing picture. Usually we talk about wave particle duality and all, but quantum mechanics, all of quantum mechanics can actually be shown from this quantum superposition, and you have to appreciate that it is actually a very different from classical superposition. We may use analogies, but it's actually very different. And we need to think in terms of quantum state, and the key is that quantum superposition talks about the superposition of physical states. That is the most important part. Okay. So yeah, a quantum entanglement is also just a manifestation of superposition principle for for multi-particle systems. It's nothing fundamental. What is fundamental is the superposition principle, nothing else. Okay, all of this I think I'll have to skip. And then finally we have the quantum measurement problem. Okay, just give you an idea. I don't think I did a very good job with this, but I am talking for over. Okay, anyway, I think I should stop now. But you should listen to this talk. Listen to this talk. Actually, I'll give the link in the description. Thank you so much. And yeah, I think I discussed stuff in this video, a lot of stuff. With that, let me end this video again. Maybe I talked a lot of. I could have made it a bit shorter. I should have made it a bit shorter. But anyway, let me know in the comments. Thank you.